I must say that I had the same experience as the previous two speakers. I was an undergraduate when I heard about the name of John Milnor for the first time. My professor had mentioned the name of exotic spheres in dimension 7. Exotic sphere, dimension 7, what could that mean? So I went to the professor and I said I wanted more information. And he told me you should begin by reading Milnor's books. And I went to these books, and that was like a revelation, a new world. I must say that at the time, the only math books I had tried to open were Bourbaki. So it was really a different world for me. So I think in name of thousands of mathematicians, we should thank John for his books. Thank you very much. So today, I would like to introduce you to a high-dimensional topology. I do want to stay at a very elementary level, so I will not prove anything. I will not show everything. I will just show little things. You know, my goal would be to find the secret of what's happening in Milnor's mind when he closes his eyes and thinks about 7 dimensions. You know, before we start our excursion to dimension 7, I think it's good to begin by discussing fundamental questions like, what is space? What is dimension? These are very old questions in philosophy of knowledge. And, you know, typically mathematicians are not interested by philosophy. But allow me a little bit to remind you some of the main ideas in the philosophy of the nature of space. I will mention a few theories. We mathematicians are all basically sons and daughters of Newton. Newton was a realist. He believed that space is three-dimensional, exists physically, and objects are within that space. If you think a little bit, you immediately understand that this is not so easy and obvious. If you pick a point in space, x, y, z, and if this space is a region of space where it's empty space, how could there be a point if the space is empty? So even the concept of empty space was problematic. And there was a big discussion between Newton and Leibniz. It was really a fascinating discussion. Leibniz did not believe in the existence of space. He said that space was just relationship between objects. You see, it's something like a family. A family is not just the list of its members. A family is a structured set. It's people and relationship with them. For Leibniz, space is this, is the relationship between objects. So somehow this concept of space in the mind of Leibniz is very close to our modern concept of metric space. A metric space is a set of points structured by some additional information, which is the distance. And then came the great Immanuel Kant, the great philosopher. Immanuel Kant is neither a realist nor an idealist. His point of view is that all of us have in our mind preloaded when we come to Earth, when we have preloaded some a priori concepts which belong to the human beings. And among these concepts, the concept of Euclidean three-dimensional space. This does not mean that Kant was thinking that the space is three-dimensional. What Kant is saying is that when my brain is receiving information from the outside world, all this data, all these informations which arrive in my brain are interpreted, are understood in the framework of this built-in three-dimensional geometry. So my mind contains the concept of three-dimensional geometry. It was there when I was born, and I received information from the outside world, and I understand it in these words. But never Kant would say that the world is three-dimensional. I understand it through three-dimensional concept. I am unable to give a talk without mentioning the name of Poincaré. Poincaré, by the end of the 19th century, wrote a wonderful paper on the philosophy of space. What is space? Everybody should read it. Actually, it's one of the very few papers that he wrote in English. Poincaré is a realist. The physical world exists. But unlike Kant, he would not say that when we come to this life, we have Euclidean geometry in our mind. The a priori concept that belongs to human beings is not three-dimensional space. The a priori concept that we have, all of us, that we share, is the mathematical concept of groups. But groups, plural, meaning that it is through experience between my body and the external world that my mind will progressively select the correct group which is best suited to understand what's arriving to me. So this is higher level thinking. For Newton and Kant, the space is three-dimensional because God created it this way. I'm sorry, for Newton and Leibniz, God created it this way. For Kant, it is three-dimensional because God created my mind in this way. Okay? For Poincaré, it's very different. My mind selects the group which is convenient to understand my world. Let me explain that a little bit more. This is when we, in our everyday life, frequently we see things which are changing locally. Let me give you a very simple-minded example. You have this chessboard, and something is happening in the middle. A horse is rotating. When you see this little animation, because you had similar experiences when you were a child, or maybe because your ancestors had similar experiences, you know, your brain knows that you can counterbalance this change by a motion of your body. If you rotate around the chessboard, you know that the horse does not move. So I know that some motions of my body are able to counterbalance some changes in my perception. Of course, the same change of perception can be counterbalanced by several different motions. I could rotate this way, or I could rotate this way, or whatever. So this gives some equivalence relation in the space of motions of my body. And the corresponding quotient space is a group, which is the group of symmetries of space. And my brain has built in the concept of group. So my brain will select the group which has been selected through experience. Experience being interaction between the outside world and my own body, my own mind. So Poincaré gives many examples. One of them is this. Why do we commonly say that our visual space is three-dimensional? Well, if you think a bit, you see that on our retina, the images are two-dimensional. But we have some additional information for distances. I can use the binocular vision, but I can also use the accommodation of the muscles of a single eye to detect distance. It is an experimental fact that these two ways of measuring distances are the same. Poincaré says, let's imagine that we would be some kind of aquatic creatures. We would be swimming in some ocean. And assume that the ocean has a refraction index which is non-constant. Then measuring distance using accommodation of the eye or measuring distance using binocular vision would be not coherent. That would be two different informations. And then, according to Poincaré, my mind would have selected another group. And we would decide that we will live in dimension 4. Because it would be more convenient for us to use this higher, more complicated group to understand the external perception. That's the so-called conventionalist theory in the philosophy of knowledge. There is another example that I like very much. When you receive light in your eye, the light is a wave. And this wave can be decomposed in harmonics. One harmonic for each wavelength. But this number of possible wavelengths is infinite. It could be any positive number. Hence, the space of possible lights coming into my eye is infinite dimensional. However, in the back of my retina, I have three kinds, not four. I have three kinds of captors. Each captor is capturing a specific wavelength, or more precisely, a specific bracket of wavelength. One for red, one for green, and one for blue. So that means that, for me, even though the external world is infinite dimensional, the way my brain is understanding it is three-dimensional because it only depends on three numbers. If I want to select a color on the computer screen, I give three numbers. And why three and not four? Just because of biology, because we are built this way. We have three captors, we do not have four. Look at this little shrimp. It's called a mantis shrimp. It belongs to the category of stomatopoda. According to biologists, this shrimp has the best vision system in the world. It has no less than 16 kinds of receptors on the retina. So these bugs, they live in a 16-dimensional color space. So next time you meet a friend and he tells you that he's colorblind, you should think yourself that we are all colorblind. We miss all these dimensions. This little bug would find a Milnor sphere completely trivial. They live in dimension 16. Okay, so I wanted to insist on that according to Poincaré, our brain is ready to understand any dimension. It's just a matter of experience. Experience between you and the outside world will teach you what is the space that you need, what is the group that you need. Let's have a look at what Poincaré says. It's always good to read Poincaré. Poincaré says, there is a topology of more than 3 dimensions. I do not say that this is an easy science. I have devoted too much effort to it not to have taken account of the difficulties which are encountered in it. But nevertheless, this science is possible. And it does not rest exclusively on analysis. So those of you which think that n dimension is just n numbers are wrong. Analysis is not enough to understand topology. It could not be pursued successfully without a continual appeal to intuition. Therefore, there is surely an intuition about the continua of more than 3 dimensions, and if it demands more sustained attention, it is doubtless a matter of habits. Do we not see in our high schools pupils who do well in plane geometry, but we cannot visualize space? It is not their intuition of 3-dimensional space which is lacking, but they are not in the habit of using it, and they need to make an effort to do so. So again, 3-dimension, 4-dimension, 7-dimension, 16-dimension is just a matter of experience. I shall conclude that there is in all of us an intuitive notion of the continuum of any number of dimensions, whatever, because we possess the capacity to construct a physical and mathematical continuum. And this capacity exists in us before any experience. It is the exterior world, it is the experience which induces us to make use of it. So you can think of something like languages. Babies do not speak any language, but they have the ability to learn language. Babies do not speak any dimension, but they have the ability to understand group theory. Okay, enough philosophy. Let me now go a little bit to history, not of philosophy, but mathematics. How the geometry and topology in n dimension began and how it was accepted gradually. Well, there is little doubt that the first fundamental step was done by Riemann. In his habilitation in 1854, he created the concept of manifold. A manifold for him is a space which is locally described by n numbers. But he's very careful. He does not say that these numbers are part of the manifold. These numbers are tools to understand the manifold. You use the numbers or coordinate to see them, just in the way when you want to understand an unknown territory, you construct an atlas. So the coordinates of the countries on the atlas are not part of the country. They are just tools to understand them. So Riemann understood that very clearly. There should be a distinction between the manifold itself and the coordinate system we use to look at it. So that was 1854. Riemann was following the path of his master, Gauss. Gauss was very much interested in geodesy. He produced a map of the northern part of Germany. You have here a triangulation used by Gauss, and many of you know the role of triangulations in topology today. In producing this map, Gauss had an incredible number of great ideas from the practical point of view and also from the theoretical point of view. He invented so many things like curvature, the use of complex numbers, conformal coordinates. It's just amazing. Another fundamental idea that one finds in Riemann, which for us today is like obvious, but at the time it was very difficult, is to make a clear distinction between topology and geometry. Geometry discusses length, angles, tangencies. Topology deals with qualitative properties. Like, for example, you have a curve, you have 3 points on that, A, B, C, and you may say the point B is in between A and C. This is topology. If you say the distance between A and B is 3 meters, this is geometry. So Riemann made that very, very clear. And I wanted to choose 2 examples to show you the difference between topology and geometry. I just want to give 2 examples concerning the 2-dimensional sphere. The first, I will call it the Poincaré conjecture in dimension 2, except that it's not a conjecture because it's just a theorem, and of course, Poincaré knew that very well. You have here a picture which many of you could think it is extracted from the book of Milnor on Morse theory. But no, it's a picture from Möbius in 1860-something. And in this, he proves, with a completely rigorous proof, that if you have a surface which is compact, and if every loop on it can be shrunk to a point, then this surface has to be homeomorphic to the 2-sphere. This is topology. Homeomorphic means you can find a correspondence between this shape and the standard sphere, which is continuous as well as its inverse. This is topology. Now, let me give you an example of geometry. And for this, I chose a conjecture that I'd like to call Milnor's conjecture. Indeed, this is a conjecture of Milnor that he made more than 50 years ago, which is still open today. And I checked on the internet. This seems to be the paper of Milnor with the least number of citations. Nobody read it, obviously. 2 people, 2 citations. So maybe this conjecture is still open because nobody read it. But so maybe tonight we have a solution. Okay. So here's the geometrical conjecture of Milnor. This is not Milnor. Okay, so this is a question about cartography. You have a domain on the Earth, like the red zone here. You assume that this domain is convex, and you look for a map of it. And a map would be a map from the domain to the plane, and you would like this map to be as isometric as possible. You would like this map to have a scale which is as close as possible to 1. And the conjecture of Milnor is that if the country is small enough, that should be possible with a good scale. So let me give this exact statement. For every convex domain on the sphere, contained in some hemisphere, there should exist a map, in the cartographic meaning of it, there should exist a map from the domain to the plane such that the scale, the ratio of the distances measured in the plane and measured in the sphere, is sandwiched between 1 and exponential of epsilon, where epsilon is the relative area of the country relative to the full area of the Earth. So if you have a country, he gives the example of the USA, big country, 1.5% of the Earth, should be representable on the plane with an error of 1.5%. What is not? Oh, yeah. This is why, I mean, I think Jack knows that it's not convex, and he says, take the rectangle containing it. And now this is 2%, okay? Okay, this is geometry. It is not clear to me that Riemann tried to practice his mind, to think topology in higher dimension like Poincaré was suggesting. If you want to study n-dimensional topology, you have to practice. Just like if you want to play the violin, you have to practice. If you want to do any serious thing in mathematics, you have to practice. And I'm sure that Jack practiced a lot. And the idea is that you should create your own mental experiences, to create your own little group of high dimension to get some feeling about space. It took a long time before people understood that the n-dimensional topology or geometry could be understood. Many people worked on that. I wanted to single out one person. This one person is totally forgotten for some reason that is unacceptable. The name of this woman is Alicia Boole. Alicia Boole was the daughter of the logician Boole. And the logician Boole, 1940, this is backwards in time. Huh? This is 1940. So Alicia Boole was the daughter of the logician Boole. But unfortunately for her and for her father, he passed away when she was 4. And she had no mathematical education. At the time, it was not easy for a woman to be a professional mathematician, still today, and she was only an amateur. She was a professional secretary. And all her life, she worked on understanding the geometry in dimension 4, but understanding meaning with her hands. So for example, she's the first who decided to create paper model of 4-dimensional objects sliced by hyperplanes in dimension 3. So somehow you would think of the 4th dimension as being time, and you would think of a picture in dimension 4 as being a movie where you slice it by parallel hyperplanes. And she did that. She wrote several papers, and these objects have been preserved in Groningen. And at the end of her life, she got a honorary degree from the University of Groningen. But really, I think she was the first who said, yes, you know, something like Thurston style. I want to see things. So she wanted to see things and to create things in practice, and she did it. But she, of course, she's not the only one who tried to understand high dimension in concrete terms. Of course, Poincaré was also a fantastic man for that. And let me mention what he said about the n dimension. This is a text in which Poincaré is complaining against the idea that n space is just n numbers. According to him, topology should not be reduced to numbers. So he says, in order to define the continuum of n dimensions, we first of all have the analytic definition. A continuum of n dimensions is a set of n coordinates. That is, a set of n quantities capable of varying independently one from the other. This definition, flawless from the point of view of mathematics, nevertheless, could not entirely be satisfactory to us. In a continuum, the diverse coordinates are not, so to speak, juxtaposed one to the other. They are linked among themselves so as to form the various aspects of a whole. At each instant in the study of space, we carry out what is called a change of coordinates. This definition minimizes the importance of the intuitive origin of the notion of continuum and the rich ideas which this notion contains. It recurs in the type of definitions which have become so frequent in mathematics since the tendency to arithmetize this science. These definitions could not satisfy the philosopher. I do not mean that this arithmetization of mathematics is undesirable. I say that this is not everything. Okay, so now it's time to travel to the 7th dimension after these long preliminaries. Actually, if I Google seventh dimension, I found some travel agency. It's a travel agency to the Holy Land. So I'm proposing you some kind of tour to the Holy Land. Okay, so we will not go very far away. We're going to just to the seventh dimension. I will show you the sphere of dimension 7. I will show you the exotic sphere. I will tell you why this is exotic, and that will be the end of our tour. If you want to go further, you have to book another tour and to ask for another guide. You have plenty of them here. Okay, so I will use analogies. We're going to try to understand dimensions one by one, so to speak. So this is a sphere, the set of points in space at distance 1 from the origin, from a point. It's already something that is not easy to understand in the common, in the general public, that people have difficulties making difference between the sphere and the ball. You know, in secondary school, many people don't make difference between sphere and ball. And this is not so easy to understand. Actually, if you look on the papers of Euler on surfaces, you see that Euler defines surface as being the boundary of a three-dimensional object. So all manifolds for Euler are cobordant to 0. So let's begin by the easiest sphere, dimension 0. So this is the line. And we look at the set of points at distance 1 for the origin. So you have only 2 points, +1 and -1. The set of real numbers whose absolute value is 1. Well, there is not much to say about this set of 2 points, except the important observation that this is a group. If you multiply 2 elements of the set +1, -1, you still have an element of the set +1, -1. So the sphere turns out to be a group, even though it's only 2 points. Now let's go in higher dimension. The sphere in the plane that we call circle, this circle turns out also to be a group. You know, you can detect the position of a point on the circle by some angle theta. And if you have 2 points, θ1, θ2, you just can add the 2 angles, θ1 plus θ2, you have a third point. So the circle, and this is a fundamental fact in mathematics, the circle is a group. A good way to see that the circle is a group is to think using complex numbers. You know, complex numbers are linear combinations, x plus iy, where I is this imaginary number whose square is -1. And we have this little miracle that the modulus of the complex number, that is the distance to the origin, is multiplicative. The modulus of the product is the product of the moduli, which in particular implies that if you take 2 complex numbers with modulus 1, the product has modulus 1. So indeed, the circle is stable under multiplication. This is really a simple but fundamental fact. Now let's go to dimension 2. Dimension 2 is our Earth. But you know, this picture is familiar to us now, but was not familiar to my father, because nobody could see that before 1969. Huh? So, oh no, before, when was the first rocket? 60, well, anyway. During a long time, in order to understand geometry and topology on the Earth, on the sphere, we needed maps, charts, atlases. And one of the most famous atlas and the most famous map to understand the Earth is the so-called stereographic projection. You project the sphere to the plane by this, as shown on the picture, and you see all the sphere except the North Pole is projected to the plane. So you can identify the sphere -1 point with the plane. And if you think of the plane as complex numbers, you can think of this as being one-dimensional, even though it's two-dimensional. But you can think it's one-dimensional because you only need one complex number to describe it. So really, it's an exercise you have to do always if you want to progress. You have to switch in your mind between real numbers and complex numbers. You have to switch between the zero sphere and the one sphere. You have to switch between the plane and the line. This plane, this blue plane, is a plane over the real numbers, but it's a line over the complex numbers. So this kind of exercise, mental exercise, you have to do that frequently if you want to climb the mountain of seventh dimension. You have to be familiar with the difference between S0 and S1. Both of them are groups. They are not quite the same, but they have similar features. You have to be familiar with the analogies between the plane and the line. Both of them are dimension 1 and 2, depending on real or complex numbers. You have to be careful. Now, this stereographic projection is a real wonderful object. In particular, it enables you to identify the sphere that you see here with the so-called Riemann sphere. It's, if you use coordinates, complex numbers on the plane, the Riemann sphere will be identified with complex number union infinity. So again, this is something you have to keep in your mind. The sphere somehow is a line. The sphere is a projective line over the complex numbers. And this exercise, this mental exercise, has to be continuously performed in your mind if you want to progress. Now, unfortunately, the two sphere is not a group, unlike the zero sphere and the one sphere. There is an interesting story about that. The two sphere would be a group if we could multiply vectors in free space, just like we can multiply vectors in R2. Vectors in R2 are complex numbers. If we could multiply vectors in free space, the two sphere would be a group. And then there is an anecdote that Hamilton, not Richard Hamilton, William Hamilton, in the 1840s, was trying to multiply vectors. And he says that every morning at breakfast, he would say to his sons, the sons would say to him, "Daddy, can you multiply vectors?" And Hamilton would answer, "No, sons, I'm sorry, I can only add them. I cannot multiply them." And all of a sudden, I think the 16th of October of 1843, Hamilton understood that he could multiply vectors not in dimension 3, but in dimension 4. He had invented quaternions. So his idea was to create abstract objects analogous to complex numbers, except that we use x0 plus x1i plus x2j plus x3k, where I, j, k are three imaginary numbers. And then you impose that the squares of them is -1, and the multiplication table is given there. Ij is minus, Ij is minus ji is equal to k, etc. And he discovered that if you play this game, you still have the same miracle, that the modulus, the distance to the origin, is the product, is multiplicative. Modulus of product is product of moduli. He discovered that. Which implies in particular that if you go to the three-dimensional sphere inside R4, it is a group again. Now, it's a non-commutative group. I should say non-abelian group here. So this non-commutative group is the three-sphere. And when you have a non-commutative group, you can multiply on the right or on the left. And they are different things because it's not commutative. So that the three-sphere inherits a huge number of symmetries, left and right. Remember once Thurston told me the the three-sphere is the roundest, because the group of symmetry of the three-sphere is bigger. So look at this picture. It is the same as before, except that I changed letters. The two axes, Z1, Z2, are now complex numbers. So you should think, you should wink a little bit, and you should realize that each axis turns out to be a complex line, real plane. So this axis Z1 turns out to be two-dimensional, and the Z2 is also two-dimensional. So 2 plus 2 is 4. So indeed, we are in four-dimensional space. And we have this unit sphere sitting inside R4, inside C2, inside H, Hamilton quaternions. So here's a picture. This picture is a line. The equation is simple. Z2 is A, Z1. But A, Z1, and Z2 are complex numbers. So you have this line. The blue line, you should think of it as being one-dimensional. It's one-dimensional in my picture, but it's complex one-dimensional. So it's two-dimensional object. The red line is also two-dimensional, and the orange one is also a complex line. So it's two-dimensional. So if I look at the unit sphere in R4, it will intersect each one of these lines on a sphere in the line. But a sphere in the line will be a sphere in a two-plane. So it will be a circle. So for every value of the complex number A, I have a circle. This circle is a circle inside four-dimensional space. So this is a trick by which you can construct many, many circles inside the three-sphere. So these circles are called the Hopf circles. So let me show you some of them. So for each one of these circles, it corresponds to some line. Z2 is equal to AZ1, intersecting the three-sphere on a circle inside this line. The line is one-dimensional over the complex, is two-dimensional over the real number. So this is the so-called Hopf fibration, which is so important for topologists. This is a projection from the three-sphere to the two-sphere, such that the inverse image of every point is a circle. So here this very nice picture connecting three-sphere, two-sphere, one-sphere. Now, what's happening if you go to a higher dimension? Oh, not yet, not too fast. Not too fast. Here I take two lines. Z2 is equal to AZ1, and Z2 is equal to BZ1. A and B are two complex numbers. And you see on the lower left side, you see A is the complex, is the point, the green point, and B is the red point. And then you have a C now. So you have three lines intersecting at the origin. And when you have three lines intersecting at the origin, this creates this picture, the Hopf links. So next time you see two lines intersecting like that, do not think it's a stupid picture. It contains a lot of topology if you think of these lines as being complex lines. Okay, so what's about, that gives me the opportunity to say a few words about a contribution of Milnor on singularity theory. We had that in the previous talk, but let me show you that. Suppose you have two lines, x is equal to 0, y is equal to 0. You want to understand that. So if x and y are real numbers, not much to say. But if x and y are complex numbers, you can play the game of saying, well, let me look at the map from the three-sphere minus the line, the two lines, x is equal to 0 or y is equal to 0, to the circle where you map x, y to the argument of xy. So xy divided by its modulus. It's a map from the 3-sphere minus the 2 lines onto the circle. This is called the Milnor's fibration. And if you take a point in the circle, take the inverse image, you see pictures like that. Here you have 2 Hopf circles corresponding to 2 lines, and the green surface that you see here is the inverse image of 1 point on the circle by the Hopf, by the Milnor fibration. Here's another picture, and here's another. If you take 3 lines, you have this kind of behavior. So you can really understand the behavior of algebraic curves, or is here is a very simple case of lines, in terms of topology. Now we have been from dimension 0, 1, 2, 4. Of course, it's very tempting to go to dimension 8. And this is exactly what Graves and Cayley did right after Hamilton. They created octonions. Octonions is the same game as complex numbers. You have these quantities. It's x0 plus x1 e1 plus x2 e2, etc., plus x7 e7. And you have this complicated multiplication table. And again, you have this miracle that if you take the modulus, the distance to the origin, this is multiplicative. So you would like to say that the 7th sphere, here we are, the 7th sphere is a group. But this is not true. This is not true because octonions are not associative. So it's not quite a group. This is something topologists call a H-space, H in honor of Hopf. It is close to a group, but it's not a group. But nevertheless, this helps us understanding the 7th sphere. The 7th sphere sits inside the octonions as the unit elements in the octonions. So if you say real numbers dimension 1, complex number dimension 2 but dimension 1, quaternions dimension 4 but dimension 2 over the complex numbers. So quaternions are dimension 1 over themselves. So you could say the octonions have dimension 1. So somehow octonions is a one-dimensional object, and the 7-dimensional sphere is a 0-dimensional sphere. So, you know, you should play this kind of game and trying to analyze the analogies, differences, understand the influence of associativity, commutativity. You have to make your own experiences between experience and your own mind. And of course, this takes time. I mean, that would not take 45 minutes to do that. We can play the same game with the 7th sphere, except that instead of having Z1, Z2, now you have Q1, Q2. Each axis is now 4-dimensional. Each axis is a quaternion. So we can play the same game for each A, but now A is a quaternion. We have a line. This line is 4-dimensional. This 4-dimensional line will intersect the sphere on a 3-dimensional sphere. So really you have the same picture as we had, but I cannot show you a film now. You have the Hopf fibration, which goes from the 7th sphere to the 4th sphere, and the inverse images of points are 3 spheres. So again, you need to practice. You have to close your eyes. Animations are not enough anymore. You have to work at night. It's much better. And then you say, well, maybe I can go from 1, 2, 4, 8. Why not going on to 16 ions or 32 ions? And then there is a wonderful theorem of Kerver, Bott, and Milnor, 1958, which says that the story stops there. And the exact statement is this. If you try to multiply vectors, so if you try to multiply, you look for a multiplication from Rn cross Rn to Rn. And you just want one condition. You want that the multiplication of 2 non-zero vectors is non-zero. With this assumption, you can prove, I mean, Kerver, Bott, and Milnor proved that indeed the dimension of n has to be 0, 1, 2, 4, or 8. This is a wonderful algebraic theorem whose proof is totally topological. It's a wonderful, I like this very much. But this is, even today, it's a very difficult theorem. Okay, so we have seen the seventh sphere. Now it's time to go to the exotic sphere and tell you why it is exotic and what it is. So if you want to describe the seventh sphere, there is a simple way to do it. I will use two coordinates, Q1 and Q2. Each one of them is a quaternion. So from time to time, you think Q1 as being one-dimensional, four-dimensional, two-dimensional, depending on your mood. And then you say, well, let me try to cut the sphere of dimension 7 in two parts. I can decompose it into the part where Q2 has a modulus less than Q1, and the second part where Q1 has a modulus less than Q2. So this gives a decomposition of the sphere of dimension 7 in two blocks. Each one of the two blocks can be easily described, because if the modulus of Q2 is less than the modulus of Q1, then you can set x is equal to Q2, Q1 inverse, and x has modulus less than 1. And then you can define y to be the argument of Q1, Q1 divided by its modulus. So the first part, part 1, where the modulus of Q1 is less than the modulus of Q2, this first part is described by pairs of quaternions. The first x being of modulus less than 1, and the second y being of modulus 1. So the first part actually is the product of a four-dimensional ball and a three-dimensional sphere. For the second part, you play exactly the same game, except that you put some conjugate. And these two parts intersect on the boundary, and you look at the change of coordinate there, and it's a very simple exercise to see that the change of coordinate is given by some simple formula. On the common boundary of these two blocks, you have identification between xy and xy. This gives you a recipe to construct a seventh sphere. Well, you need ingredients. You need two 4 balls, B14 and B24. You need two 3 spheres, S13, S23. Then you form the product of the ball and the sphere, of the ball and the sphere, and then you glue the two boundaries according to the rule I just mentioned. You glue xy and xy. You glue that, you get a seventh sphere. Now, what was the idea of John Milnor? To construct an exotic sphere. Well, not just like in good cuisine. You just take a well-known recipe and just change it just a little bit something. What he did is just change a little bit the gluing map. Instead, you just start the same way. You take two 4 balls and two 3 spheres. You multiply them just as before, but when you glue, you change just a little bit the identification. Instead of gluing xy with xy, you glue xy with x2, y, x inverse. Why? Don't ask me, ask him. So you just glue the things in a different way. And what Milnor proved is this manifold that you get is homeomorphic to the seventh sphere and is not diffeomorphic to the seventh sphere. Homeomorphic, I told you, that means that there is a correspondence with seventh sphere which is continuous as well as the inverse. Now I should tell you what it means to be diffeomorphic. Let me show you an example. This is a square. And let me show you a diffeomorphism. So why do I call that diffeomorphism? Because if you select a point, and if you zoom in this, around this point, let me select the right eye, you see that the map looks almost linear. This little square in green is mapped by this ugly deformation into something which looks like a parallelogram. If I had chosen something smaller, the image would be even closer to parallelogram. So diffeomorphism means that if you zoom enough, your map is better and better, looks more and more linear. Now let me show you something which is not diffeomorphism. Poor Jack. You see, if I zoom, the situation is bad and bad and bad again. The situation will not improve. This is a homeomorphism. So homeomorphisms are dealing with qualitative property, and diffeomorphisms are linked with this local good property. So why was this theorem of Milnor that this exotic sphere is homeomorphic but not diffeomorphic, why was it a shock for topologists in 56? Well, several reasons. One of them is that you know, the big shots of the time could not believe it could be true. I found a letter from Poincaré, my hero. Poincaré, rather old, writing a letter to the young Brouwer. Brouwer was pointing to Poincaré that, you know, homeomorphisms and diffeomorphisms is not the same game. It's more complicated. And Brouwer was explaining that it was not obvious that it was not obvious that two manifolds which are homeomorphic have the same dimension, for example. And the letter of Poincaré is arrogant. The answer is really arrogant. He just says, just smooth it. For him, homeomorphisms and diffeomorphisms were just the same thing. So he was wrong. And he was completely wrong, and we know why now, because of this seventh sphere. So let me say just maybe a bit more why this was shocking. It was shocking because everybody knew a proof that it was not true. So if you take a continuous map, this is continuous function, like a stock market or something. You want to make it smooth. Well, there is a very well-known way of doing it. You just average it. You choose some epsilon, and for each value x, you replace your function by the average on a small interval centered at x. In formula, you write f epsilon x is just the average of f on a small interval. And if you do that, I mean, statisticians do that every day to smooth the variations, the noise in the signal. And if you do that, you see the non-smooth function immediately becomes very smooth. And eventually is constant, actually. So it's a way of smoothing things. And it is completely clear that you can do the same game with homeomorphisms. You have a homeomorphism from the plane to the plane, from space to space. You can smooth it. For each point, you take the image and you average the image on a small box around x. And it becomes smooth. But the point that nobody understood is that this smoothing might lose the bijectivity. It might not be a bijection. Let me show you that. This is an even worse homeomorphism. Okay, so this is bad homeomorphism. Now let me smooth it. So I computed the average of this map using some epsilon. And the result is this. You see, after the smoothing, Jack has one more eye. Yeah? 2 points are mapped on the same eye, which means that the smoothing was not successful. The smoothing was not a bijection. So this wrong proof that everybody believed it should work does not work. Well, I think my time is over, I think. I'd like to finish by showing you the seventh sphere. So I decided to do the following. This is a white ball with the light of a flashlight rotating around it. You might think this is the moon, and these are the phases of the moon. But this moon is two-dimensional. This is our moon. How would be the moon if we would live in dimension 8, and if the moon would be 7-dimensional? We would look at the moon. How would it be? How would be the what?
The moon is two-dimensional. You mean the surface is two-dimensional?
Yes, the surface of the moon is a two-dimensional sphere. Okay, so my question is, how would look the moon if we would be in dimension 8 looking at the moon and projecting it on our retina? So I give you the answer. I did the computation. So on the right, this is a standard moon. And on the left, you have the 7-dimensional sphere. And you see that it does not look like our moon. This is a phenomenon which is very well known in differential geometry, which is called concentration of measure. In very high dimension, spheres have a tendency to concentrate near their centers. So you see, if we would be in dimension 7, you would look at the moonrise, it would be very different. So I suggest that this night you just close your eyes, you don't sleep, and you practice this rise of moons. And you try to understand how it is dimension 2, 3, 4. How would it be in dimension 1 million, for example? How would that be? And what is a moon of infinite dimension? How is the distribution of light? That's OK. So thank you very much.